Hello, everyone. My name is Yoshisuke Ueda. As you see, I am an old man. I will be at the age of 88 soon. I am greatly honored to have been given this wonderful 2024 NSC Lagrange Award. I would also like to thank you for hosting the award lecture. This lecture should be given at a venue in Yibin, Sichuan, China. But for various reasons, I will not be able to attend. Please accept my apologies for any inconvenience caused. I will now begin with an abstract of today's talk. The study of chaotic phenomena would not be possible without the development of computer science and technology. Chaotic attractors drawn from computer outputs have taught us a lot about exact solutions of deterministic ODEs, but not enough yet. My talk today will present a view of the speaker that may contribute to the understanding of the structure of chaotic attractors. The contents of this lecture are not generated on the basis of theoretical considerations alone, but is the record of listening to what numerical experimental results tell us. Nevertheless, the written text does not appear to be entirely free from misunderstanding or misinterpretation by those interviewed. We would ask the audience to bear this concern in mind and judge the contents of the speeches strictly on this basis. I will end my preface here and now begin with the main discussion. Today's talk, the following Duffing's equation was the subject of the experiment. Second order ordinary differential equations, where K is damping coefficient and B is the amplitude of forcing signal. The mapping or transformation defined by the solution of this equation is henceforth denoted by T. Detailed numerical experiments were performed for the system constant values K equals 0.05, B equals 7.5. The following is a brief history of the process that led to the selection of this constant value. This chart, the KB chart, represents the region of occurrence of various steady oscillations drawn by analog computer experiment. The chaotic attractors are observed in the shaded area. Michael Thompson, University College London, and Bruce Stewart, Brookhaven National Laboratory, called the point K attractor Ueda's chaotic attractor in 1984. And David Riel, IHES France, called the point O attractor, Japanese attractor, 1980. Omit this. Next, we will now show you a video of emergence process of the UCA. This is a stroboscopic point sequence representation of the computer solution pursued from a single initial point. Note that the ratio of the unit length of the x and y axis is 5 versus 1. Watch the process of UCA emergence. The increasing number shown at the bottom of the animation is the number of stroboscopic observation points in that instantaneous short interval. Okay. From the way the UCA is drawn, it can be inferred that the stroboscopic observation point appear on an infinitely long curve. The alpha branch of the fixed point described below, that is infinitely folded and fractally stacked. Or conversely, the infinitely increasing observation points draw the above curve. In other words, we now have an outline, size and shape of the point set that represent the attractor. Furthermore, as you can easily infer from the UCA generation process with a time of 2 pi period seen in the previous slide, even if the observation time interval is changed to 4 pi, 6 pi, and so on, the outline of the drawing attractor remains the same, although the observation time becomes longer. I omit the performance of the actual example. On academic terms and a brief history, please note in this talk that the academic term described here were used around a century ago and are different from the academic terms used in recent dynamical systems theory. This is the very notation used in the paper of Barkov and Smith and others, which I studied with great difficulty more than half a century ago. From this point on, we will express the expressions we have been using in everyday language, in the academic language, used in the technology, in the theory, and contrast the two as we proceed with our discussion. The stroboscopic observation point sequence is represented as the positive half sequence, the right half of the complete sequence of the point P0, where P0 is the initial point. Here, the stroboscopic point sequence is the result of numerical experiments, whereas the positive half sequence is the exact solution of Duffin equation. Please keep in mind that in numerical experiments, the inevitable effects of small uncertainties cannot be avoided. The animation of UCA shown earlier is a result of a numerical experiment using the fourth-order Runge-Kutta method. This experiment does not take into account fluctuations in the constant values or nonlinear characteristic of the system. In other words, structural stability was not verified in the experiment. Then and now, to what extent should we consider fluctuations in the constant values and nonlinear characteristics of the system is a difficult question. I called this phenomenon the randomly transitional oscillation half a century ago, but it was a little longer ago I first encountered a puzzling and strange oscillating phenomenon. The experiment took place in 1961 when digital computers were in their infancy. Computational power was poor, and the computer's input-output device was not user-friendly. I was working on frequency entrainment phenomenon in a slow analog computer with one external forcing term period 2π set to 31.4 seconds. During the experiment, I encountered a strange out-of-sync oscillation phenomenon that could not be regarded as a quasi-periodic oscillation. My encounter with this phenomenon was due to good luck, but I realize now that greatest piece of luck was that the people around me were not at all interested in it. I'd like to add one more thing. I was continually frustrated and patient with the slow operation of the analog computer at the time. However, I realize now that it was a valuable time for me to keep asking myself the question, what kind of mechanism could cause such a phenomenon to appear? Theoretical description of the UCA. Here, I would like to rewrite the definition of UCA, which the author has been insisting on for many years. I have taken it for granted that I did not need to write it, but I was concerned about whether or not it is widely accepted by the researchers. The chaotic attractor UCA is defined in the exact solution sense to be the closure of the alpha branch of a directly unstable Higgs point there on the UCA. To be sure, I repeat, Higgs point alpha branch is in the sense of the exact solution of Duffing's equation. The existence of such solutions are guaranteed by a series of well-known fundamental theorems of ODE. New problems created by the replacement. The following is a list of problems that arise when the common terminology is expressed in the theoretical terminology. What is the relationship between the real stereoscopic point sequence, and the positive half sequence of point P0 is the real stereoscopic point sequence, an approximation of the theoretical UCA, even though we think it is impossible that there should be no relationship. Is the theoretical UCA a complete sequence of point P0? Is the theoretical UCA a complete sequence point P0 with its limit set, that is a closure of alpha branch, and so on? A careful step-by-step discussion is not good for the time of this lecture. It is obvious that hasty and coarse explanation will lead to a state of confusion. Therefore, I will put the discussion on the back burner and begin with the conclusion of today's talk. Nevertheless, if you do not understand the meaning of very basic academic terms, you will not be able to understand what we are talking about. As such, we ask that you look up the definition of academic terms that you do not fully understand on your own. As I wrote above, the chaotic attractor in the exact solution sense is defined as a closure of the alpha branches of the directly unstable fixed point D on the UCA, and the UCA that the experimental result represent is the set of stereoscopic observation point seen earlier. The request from the speaker. The conditions under which stationary states represented by mathematical expression or sequence of numbers appear as real phenomena have been studied since the early days of nonlinear oscillation theory. In particular, existing structural stability does not seem to distinguish between ordered and chaotic phenomena. This may be inevitable, since chaotic phenomena were known and approved at the time when they were not recognized. However, the structure of the attractor is fundamentally different. Please inform us if there are any research reports written from this point of view. Summary up to this point. The stereoscopic point sequence shown by the experimental result is the output of the computer solution pursued from a single initial point on a predetermined steady orbit. And the shape of the real chaotic attractors is reproduced the same form for each run of the experiment. This is a result of computer experiment. However, the theoretical discrete sequence traced from a single initial value can only be a proper subset of the theoretical UCA and does not depict the whole region of the UCA. The theoretical UCA consists of fixed points, periodic points, recurrent points, and doubly asymptotic points. Each of these elements is sometimes collectively referred to as a central point on the UCA. However, none of the above elements are isolated. None of the central points are isolated. Conclusions. So much for the setup. Here are conclusions or hypotheses that the author would like to express today. The real state point is two real numbers of finite digit obtained from numerical experiment. The theoretical state point is the central point of the theoretical UCA. The neighborhood of this point contains an uncountable infinite number of periodic points, doubly asymptotic points, and wandering points. Moreover, these doubly asymptotic points are the set of initial points connected to any saddle-type periodic point of the UCA, regardless of the radius of the theoretical disk. Furthermore, although we have noted the periodic point of the UCA, there may be additional recurrent points here that are different from the periodic points. In my personal opinion, such recurrent points do not exist. Also, the set of doubly asymptotic points of the UCA, where there exists also special type doubly asymptotic point, contact point of alpha and omega branches. This is not the end of my talk, but I will end the first half here for the time being. If you have time and interest, please listen to the second part. Acknowledge. I would like to express my deepest gratitude to Associate Professor Dr. Yoshihiko Suzuki. He is younger than me, more than 40 years, and Mr. Natsuki Katayama is younger than more than 60 years. Their help, I would like to express my thanks to their help in preparing the PowerPoint animations and video of my lecture. They are both at Kyoto University. I would like to express my deepest gratitude to them. Thank you very much. The following is the URL related to today's topics for your reference. The first one is written recently, and you can understand the more carefully written in this URL. And second URL is a collection of my research papers. I would now begin with the second half. There is no end to the discussion and considerations that lead to the conclusions presented above from the result of the numerical experiments. Rushing to explain ambiguous loses the credibility of the conclusion. I am well aware of this danger, but I dare to try. For more information, please refer to the URL above. Summary of numerical experimental result. The figure depicts the directly unstable fixed point day of the UCA and its alpha and omega branches on the real UCA. The upper figure should be drawn together with the lower figure, but in your mind, move it directly downward in parallel. The square is this is inversely unstable fixed point. As the figure shows, the alpha branch is a central axis corresponding to the backbone of the attractor. The figure shows the alpha branch and omega branch extended to some extent and shows the outline of the homoclinic structure composed of the invariant branches of the fixed point D. The periodic points and their invariant branches are not depicted, so there are no heteronic points in this figure. As you may have noticed from the figure, roughly speaking, the alpha branch and omega branch have a roughly top to bottom symmetrical appearance. This property becomes more pronounced as the damping coefficient K of the damping equation is decreased, and for a conservative system with K equals 0, they are vertically symmetric. See this figure. Drawing invariant branches in numerical experiment becomes more difficult as the length of the invariant branches from the fixed point D increases. This would be evident from the value of the characteristic multiplier of the fixed point D. The characteristic multiplier of the point D are 13.00037 and 0.056169. In the neighborhood of the fixed point D, the alpha branch is approximately 13 times longer for each map, and the omega branch is approximately 18 times longer for each inverse map. Even at point where the invariant branches are longer away from the neighborhood of fixed points D. The experimental result shows that the rate of branch extension does not change much. This fact makes the identification of homoclinic points or heteronic points difficult. the closure of infinitely extended, infinitely folded and fractally stacked alpha branch is the chaotic attractor, and the limit set of alpha branches contains an uncountable infinite number of periodic points and all their alpha branches. The omega branch, if extended infinitely, does not stay in the bounded region, unlike the alpha branch. It is folded infinitely like the alpha branch, but behaves as if it fills the basin of the attractor in a piano curve-like manner. In other words, the infinite extension of the omega branch is assumed to fill the entire plane. As the experiment shows, alpha branch and omega branch cross each other to form homoclinic structure, creating four type homoclinic points: A, alpha 1, omega 1, B, alpha 1 and omega 2, and so on. The figure depicts the homoclinic structure of type A. The homoclinic point produced on the alpha 1 arc, for example, on the arc between homoclinic points 0A and 0B, were produced by successively extending omega 1 branch, and the following conclusions were obtained. The homoclinic point produced on the alpha 1 arc are made by a rule similar to Cantor set rule and are distributed densely on the alpha 1 arc. This is because homoclinic points are produced with similar rules in the section of the alpha 1 arc corresponding to the central trisecting section, which is eliminated in the Cantor set construction rule. We are looking the alpha arc as the arc between homoclinic point 0B and 1A. This is a sketch of alpha 1 and omega 1 branches. The type A homoclinic structure. The homoclinic point 0A is transformed to 1A, and 2A, 3A on the omega 1 branch, and 10 to D. And inverse mapping of point 0A is image is 1 minus 1A, and the image of inverse map is minus 2A, and so on. And between the 0A and 1A arc, another homoclinic point 0B appears, and image of 0B by mapping T is this point 1B, and inverse maps of 0b is minus 1b here, and minus 2b here, and minus 3b here. Okay? This is a schematic diagram of this part. And let us pay attention to this orange region and denote this region by pi minus 1a. And this region is mapped to this green region by inverse map. And this is this region, green region, denote pi minus 2a. And next, let us consider the pi minus 3a here. Dot is dot. Move to between the gaps and comes to the pi minus 3a is, you can understand in this picture. And this region, blue region, is a alpha 1 branch from D to minus 2a. And omega 1 branch, D to minus 2a. The closed curve inside this region. The image of minus 2a, the inverse mapping image of minus 2a contained in this blue region. And this blue region represent this shaded area. And minus 3a, the tail of pi minus 3a is here. Okay? This is a numerical experiment. Then, the first step, the central part, and second part, green section, and third step in blue mark. You can see the same structure of control set generation process. And central trisecting arc. There are no homochronic points in the contour set, but in this map defined by Duffing's equation is omega branch extension comes and makes this orange part, green, orange arc, green arc, and blue arc. So the type A homoclinic, this is a type A homoclinic structure alone has an uncountable infinite number of homoclinic points and a dense distribution on alpha 1 branch. However, additional homoclinic points of type B, C, and D are also added. Moreover, all periodic points except for the D, fixed point D, have the same structure. This is quite interesting and scary, isn't it? I omit this explanation. This speaks the alpha branch on page 31 with a real UCA and applies the inverse mapping to the omega branch of which depicted on page 31. If you are interested, please listen to what this figure wants to tell you. Thank you for your kind attention.